What's up, guys? This is for all the people in Wayne State, Orgo 2, and whoever else wants to watch it. So we're going to do alkylation of ammonia. It's pretty self-explanatory. Alkylation of ammonia. This is ammonia. This is an alkyl halide group, so this is the general equation here. You got ammonia, Rx. So you got an R group. Electrons from the N come and attack the C here and kick off the Br. You make this. Nitrogen has a positive charge now. Br comes and attacks the H. Electron from the H goes back here, so you have 1, 2, so the plus charge goes away, and you end up with your NH2 on the end of your alkyl group that you started with. So you got an alkyl group that you started with plus ammonia. Halide goes away, and you got NH2 that takes its place. So this is your major product. By not that much. It's like, it's more than half. So it's the major product, and that's usually what Zybuck is worried about. All right. So next, I'm gonna do Gabriel or Gabriel, or however you pronounce it. You got this this funny named guy here. I don't really know what it's, phthalimide or something like that. And you're gonna alkylate it. Whatever. Anyways, this is how it looks. So you got a base, the KOH. This is just kind of hanging out, so it's has a partial positive charge, partial negative charge here. Nitrogen has, 1, 2, 3, 4, 5, so it doesn't have a charge. But the base comes and takes an H away. This electron here goes back to the N, so you got 1, 2, 3, 4, 5, 6. It's going to have a negative charge down here. You got your potassium here, ion, kind of chilling out. So you got partially positive, partially negative. Next, you're going to take this piece that you started with, you're going to react it with an alkyl halide group. So the negative charge comes because halides are good leaving groups. Like, we all know that from Orgo 1 and infinity of halides being good leaving groups. So these electrons here, since it's negative, comes, takes the CH3, kicks off the Br, and now you're down here. So now you have your CH3 group or an R group or whatever attached to this N, the nitrogen. So it doesn't have a charge now, which is good. Happy about that. You have hydrazine, which acts as a base. It comes and attacks the double bond O here. The electrons here kick up, make O negative. They come back down like they always do. So it comes back down, and it opens up the ring here. So literally it opens up the ring. So hydrazine comes, attacks the double bond O, electrons go up, electrons come back down. When it comes back down, carbon can have 5 bonds, so it kicks off this right here, opens up the ring. Now, we're at the opened up the ring part. So now it happens.
Proton transfer.
Proton transfer happens because if you remember from a couple chapters back or whatever, we had this thing called proton transfer. That's what this PT stands for. It confused me for a second. I thought it was like H2PT because I got a whole chalkboard of stuff written up here, and this is, yeah. So anyway, you got a positive charge here on this nitrogen here, and you got a negative charge here on that nitrogen there, because this nitrogen gained an electron from this bond that used to be here, so it's negative now, and this one lost one, so it's positive now. So anytime you got that, just accept there's proton transfer that happens, meaning you're going to balance out the charges. If you got a positive and negative ever in like something like this, you're just going to take an H off because these electrons come, take this H, kicks these electrons up, makes it both neutral. So now you're down here with this. So now what happens is, this is interesting, what happens here is this end NH2 here comes and attacks the other double bond O down here. Again, what happens is the O becomes negative, the electrons come back down to the carbon and kick off this whole group here. And this is kind of like the whole point we're kind of getting at, is you'd think that we want all this, but that's not true. We're trying to get this guy off. So we're at this step now here. So since this left right here, yeah, we're trying to make a primary and mean here. So that left, and you have, this is what left, and now it has a negative charge here. So now the negative comes and takes this H away. This positive charge here is now going to be neutral because it gets this electron from that hydrogen there. And go up here, the ring's closed down here, and you end up with your happy primary mean right here, and that's pretty much what's important. That's the whole point in doing this, is to get this piece off of this that you started with in the first place. So that's it for that. What's next, Hoffman? Let's see.
Reduction of alkylates.
Reduction of alkylazides. Okay, so this is like one big flow chart. This flow chart is pretty sweet. All this that I'm explaining right now, or trying to explain, is for chapter 21, and it's kind of like a smash course, crash course, if you will. So, anyways, you start out with a benzene ring here, and you know how we have added a nitro group there, the NO2 onto the benzene ring. It was always with its nitration. So you got an HNO3 in an acid. It attaches an NO2 to the benzene ring. Now, this R group, anytime I'm talking throughout this piece here, is going to be a benzene ring for sure. It's always going to be a benzene ring. So don't try and make it like anything else. Okay, so you can have a alkyl halide or a benzylic halide, if you can even say that, with NaCN, and the Br goes away, CN comes and attaches itself there. With the same reagents that you are going to take RN3 and also the NO2 on the benzene ring. So this benzene ring with this NO2, this benzene ring with the CN, this benzene ring with the N3. You're going to reduce it with H2PT or SN in an acid, Fe in an acid. The whole point in saying all that is that this right here, this RCN, this RN3, make this RNH2, okay? When it's reduced. When you reduce any one of these three, you make RNH2. From RNH2, you can have it react with an NaNO2. Okay, no, sorry. I'm sorry.
Thank you.
I guess not. It's always been that way, but I'm being instructed that it's not, so I'm sorry. Or we don't know. Anyway, so whatever. The reagent is you have NaNO2 and an H-giving group, so an acid. So H2SO4 and water, or just think of this like H3O+, or it can be H+ and water, or H2SO4 in water, or H3PO2. This is a new one. We're not really used to this one yet. I don't think, anyway. I'm not. So H3PO2 in water, HCl water, HBr water, HI, and you get the point. So these are the reagents that can be used, NaNO2 and some hydrogen-giving group, an acid. From your RNH2 reacted with this, okay, you can go to any one of these that I have listed here, okay? And these right here are the reagents to get there. So you started out, just to recap real fast, you started out with this benzene, and you got here with the nitration. You can go here, 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 reduce it, get this, take this, react it with NaNO2, NH-giving group, and you get Rn2 right here, Rn2, all right? And you're going to have the Rn2 react with CuCN, you get RCN. Rn2 with CuBr, you get RBr. Rn2, CuCl, RCl. Rn2, NaI, Ri. Rn2, this is different because it's not just like NaF or something. It's HbF4. This is new to me right here. This is a new one. So you go Rn2, HbF4, you get RF. Rn2, there's that H3PO2 popping up again. This is kind of newer. Or ethanol. You get RH. Rn2, water and heat, you get ROH.
Oh, there's heat in this one.
Oh, there's heat in this one?
Yep.
Okay. So I tried to organize it. All the coppers here, give you these. The sodium one is kind of by itself, so I stuck that one in the middle there. And then all the H's. You got the HbF4, H3PO2, H2O. So you get the H and the H, and I hope you kind of see how I organize that. So hopefully this is helping somebody, I think. So what's next?
Okay, so we're after this one, after that one. Yeah. Let's do the Hoffman.
Okay, so we're going to do the Hoffman now. All right, the Hoffman. You have, this is a beta elimination. This is the alpha carbon here, kind of like before, like the alpha carbon is attached to the double bond to O. This is like an N. Actually, it's not like an N, it's actually an N, but what I'm saying is that this N is like a double bond to O. So this is the alpha carbon. So this is the beta carbon here. Beta. Hope you can see that there. You react with this here. So NCH3, and there's 3 of them, with this carbon group here. You're going to have an alpha carbon that's attached to the N, and a beta carbon that's attached to the alpha carbon. Okay. With the base, in heat, this is important. So this base comes, it takes the H away from the beta. This goes to elimination. Like, that should be familiar to you already. So this H here goes to the base. This electron here pops up, makes a double bond there. And you end up with this guy. And it kicks off that NCH3 group. This is a way to get to that. So it's what is that? Less substituted? Okay.
Alkene.
Less substituted alkene. So that's new. So NCH3 goes away with the base and heat and makes a less substituted alkene there. So that could be useful maybe in like a synthesis or something like that. So now, let's see, what do we do now? Okay, so we got this R group here, C, double bond to O, N with two R groups on it. Right, this is an R group. It's not, I know it's funny looking, but anyway. So you got 1, 2, 3, 4, 5. It's got no charge. C double bond O. You got the N attached to the C at the double bond O, and yeah. So to reduce this guy, use a lithium aluminum hydride and water, and it takes the double bond O away. Now, this is important. I can't tell you how many times I keep getting this little wrong in my head. When you have a C double bond O with a lithium aluminum hydride, okay, it makes COH. It does not blow off the double bond O. Okay, so this makes alcohol. C double bond O, lithium aluminum hydride makes an alcohol. Now, whenever you got a stupid N group on this thing, N, it does not make an alcohol. No. It blows away the double bond O. All gone. Okay. Next. What's next?
Okay.
Now we got this guy over here. Yeah, this is some review here a little bit. I had to look some stuff up, rather somebody else did for me. Anyway. You got this benzene ring, NH2, NO2. If you react this right here with 2Br2 with acetic acid, the BRs are going to add ortho, or para, but it's not para because para to the NH2 is NO2, so obviously we can't put it there. So we got to put them ortho. There's 2 of these, so you get 1, 2 added on to your benzene ring in these spots right here. So just maybe something to recap too. Anything that's an electron donating group is an activating. It's activator. It's an activator. Okay. Which means whatever's being added on adds on ortho, para, but mostly ortho.
It's activating those positions.
It's activating these positions. Yeah. So meaning and those positions are now activated to accept stuff that you're reacting it with. All right, now electron withdrawing is deactivating, adds meta. I don't know if this is going to be important or not. I haven't done enough problems to know if the orthopara or meta is important here in this chapter, but it might be. So I'm just throwing it out there. We all know that already,
Yeah,
I hope.
like one. Yeah.
If not, then you probably didn't pass Orlo 1. But so that's what happens with that. So no,
That's it.
we didn't do this or this.
Oh, okay. Sorry.
Got an alkyl halide group here. 2 R groups on an N. In heat. Kind of familiar here. Electrons here go and attack that C. Kick off the Br group. Br minus comes back, takes an H away, makes this.
Yep.
So kind of like
So it's exactly like this one here.
kind of like this guy over here that we
But
did.
this one's primary, that one's secondary.
Yeah, exactly. So on the one over there that we just walked away from, it's got some R groups on here. So just remember that this thing with the halide goes away. This thing gets added on. Okay. Cool. Now, one last thing I think, and that should cover all of chapter 21 that we're in here, is you got a ketone. Plus NH2 with an R group on here. A way to add this onto here is you it actually reacts by itself. So this goes here like this. I'm doing this like that, and then this goes up here like this, and this comes back down, and yeah, you end up with this. Yep. Then you can reduce it. Reduce it with H2PT. Something I noticed. All right, I'm just gonna throw this out here. Something I noticed. Whenever you got 2 H's, man, or women, you're gonna keep your double bond here. All right. If you had 1, you're just gonna have like a single. But I don't think that you can have an R group with an NH yet, right?
Yeah, when this guy adds here, electrons come down, and that's how they create that double bond.
Right. But some kind of something to know, I mean, just from before, is that if you have like an NH, it's like a single bond between the N and the C, and then you're going to have like something, like another bond happening between some carbons down there. Anyway, that's kind of off topic, but whatever. So you got a ketone plus this group. You get to here, because the N screws over the double bond O, it adds. Now, to get from here to here, you're going to reduce it with H2PT. Reducing means reducing the number of bonds between the carbon and the N, or the carbon and the O, or whatever you got there. So you're going to take one away, and it becomes this guy up here.
Or you can use the NABH3CN.
Yeah, or NABH3CN. So, you know, like how she does, you know, we're used to doing one way for our synthesis or something because we like to stick to certain stuff. Show like no magically whatever one we're not familiar with and put that one on there. So you got to be familiar with them all. So anyway, all right. So that's 21. I tune in. I plan on going over 20, going over like the Robinson, aldol condensation, Clayson, Dickerman, other stuff. All right. Thanks.